I would say.
I mean, I imagine it depends on.
I would say that they have.
But
They internally don't have a effect to.
they have to. Otherwise,
It might actually. I wonder if it has to deal with like. If we have hydrophobic methodology.
It is on the record.
Yeah, it's recording right now. So I just started it again, and it's recording that camera, plus our audio, plus the computer screen. They could use
Excellent.
that as one.
Excellent.
I think if somebody would dial in and start talking, because it's in recording mode, it would then record their video while they're talking, and then switch back to us while we're talking.
Okay.
If it's not like that, somebody dials in and they don't ask questions throughout or have any audio, it should just record our video the entire time.
But I would say internally they are arbitrary until you put them.
Thank you much, and you are very welcome to stay
They still can't like
as a special guest.
Yeah, I'll stay at least until you get
Just
started,
because
just
then
to
you
make
can
sure everything is good.
compare. Okay, this is a D. He's the orbital for the ion center. This is where it would be every mass. But that's very true. It might be,
well, maybe it is.
but not.
Yeah.
Taking two physics classes.
So,
Oh no! It's not so bad.
Oh,
Sorry that it is not a beer.
I know it's a high campus. So.
Yeah.
No, I'll take two.
I think that might. I don't.
Oh.
University of Florida is not a right campus.
University of Florida, is it?
Isn't. And
That may
at
dictate.
Friday evenings, they have a big balcony in the center of physics building, and there are like little wine parties.
How do you know this?
Because I was participating in these parties.
But for what? When were you participating? Was it for a conference?
No, just like
Oh, you had your postdoc there?
Yeah.
Who did you have it under?
huh? Nietzsche? If you well,
Okay, I think was that at UFC?
no. UF is much better than UFC. It's like tier 1. UFC is a little newcomer.
I feel as if I was gonna collaborate with him, but now I don't remember.
You think about Artyom Masumov?
Yeah, that guy.
He's same rank as Svetlana. He was a postdoc with Sergey.
Oh,
So he's not a
he's not like.
big hump above all of us.
Did you go to Penn State?
No, my brother-in-law.
So that's a good exception.
Did they do well in whatever? I was flipping
They're
through.
number 5. Apparently, I just read it today. So you want to be top 4 wins to get to the playoffs. Is that what you're talking about?
I don't know, they were playing a game, and I was flipping through, and I was like, I don't really care, but apparently they had a scandal a few years ago.
Yeah, so they had a scandal. There was one of the coaches had something. Anyway, they lost like some rights, but now they're finally able to like meet again or compete for titles.
Sure.
They actually did really well this year in the FBS, which is not what the Bison play, which is the FCS. They go for 4 playoff system, so 4 teams can make it to go to title national championship.
But isn't there only 2 teams that can play in that?
So there's a 4-man bracket. It's like in the FCS with the Bison play for. There's like 16 teams from different divisions that go. But you know the rank FBS like, is number 1, so the only top 4 teams do it.
I so much dislike all of the 19 stuff. They should just go with like 1, 2, 3, 4,
Exam should be
5 garbage.
It's scurvy now.
Or until it's crap. And 1 is the best, 2 is whatever.
Yeah, that's
Not like FBS, FCS, all that.
So there's 2 different divisions. One's football championship system, and one's football bowl system. So the bowl system, they used to didn't have a playoff system. They just
You
get a
can
bowl.
place those decorations
They
higher
were
up,
like,
but then
you get
they will
ranked
block
by
the
the
view.
computer.
Yeah, for sure. Have to raise the camera.
Computers are expert.
I think combination. I can't remember all of them. Which they still do.
Took the picture-in-picture out, see that you have the video there anyways.
Otherwise,
I'm covering it.
they get wrecked. Whereas the FCS, you rank that puts you into a seeding like for the playoffs.
And we're FBS.
FCS.
Oh.
How do you feel?
The bigger schools are FBS. There's not much of a playoff system.
So you don't get scurvy.
Yeah. Oh, I guess the tangerines.
Expect a lot of
Mine was very basic.
Well, it's the most important part of the exam.
Oh. I don't have another pencil. I have like.
Thank you.
I always seem to put them in the backpack and take them out.
I hit your hand.
I know, that was the receiver's fault.
Okay, well, thank you for coming. It is the last formal meeting of the course 46776. This is Introduction to Computational Chemistry course. The goal of the course is that students of broad background and broad background in level of advancement and in the primary subject area, chemistry, physics, biochemistry, engineering, polymers and coating, get exposure to the practical methods for computational chemistry research, so that skills acquired in this course can be accumulated towards the practical research of the attendees of this class. There was several background components, but last couple of weeks, everyone in this class was spending in doing research projects, applying their newly accumulated skills towards practical research of their interest. So the results of this research are very encouraging. They're seeds of serious research. But those who are guests, please take into account that 2-week research cannot be judged on the same level as professional research made for years. So main goal of this component, well, one of the goals of this component is to induce an appetite to computational research, so that those who are exposed in this course can continue going on if it looks interesting. for them. So the presentations are split onto 4 segments, applications. The study of minerals, study of catalytic reactions, study of nanointerfaces, and study of charge transfer. And the course itself was organized as a superposition of 3 main basis things. One is theoretical background, another is practical skill, and third, scientific communications. So, larger part of the semester, we were spending time on learning equations, building atomic models, running correct software on a correct hardware, and computing observables related to your research interests. Right now, it is time to practice scientific communications, to make write-ups, to play reviewers, and now present and survive questions. So please be aware that although we have one talk postponed, we are still very limited in time. The room is reserved for a limited time. Some of us will have exam right after this meeting. So please never overcome the 8 minutes per talk total. Out of this 8 minutes, 1 minute is to walk to the stage. 4 minutes, just 4, is to present your research. If, please note, if you are going further, if your talk spends more than 4 minutes, I will be standing here, blocking the camera, blocking you, and giving sign. Please stop. So if you are feeling that you are spending more than 4 minutes per talk, then skip something and go to conclusions. We need to be in time. It is our most important goal. Okay? And the guests, special guests, guest reviewers have an opportunity, although as all attendees of the class have chance to judge the talk, making marks near the level of presentation in several categories, like analysis, presentation, reasonable conclusions, and ask those questions that are not fit in 2-minute section for answering questions. So if there will be no questions, bad. If questions will be going too long, also bad. So please try to limit questions, and if you really want to ask the presenter, just write down near the name. Okay, with this, I would like to show you the protocol, how we do these presentations. All of your presentations are uploaded to this computer. They are numbered according to the number of presenter and named according to the name of the presenter. So you are browsing to the right presentation. 1, 2, 3, 4, 5. Click on it and bring it to the big screen. With this, I would like to announce first presenter, HM476, who will show the application of computational chemistry methods to description of optical properties of minerals. Okay? Stage is yours for generous 4 minutes.
Hi everyone, good afternoon. This is HM476. The topic of my today's presentation is VASP simulation of calcite mineral. Actually, calcite is one of the most predominant geological minerals on Earth. Actually, it is a stable form of calcium carbonate that is found on sedimentary rocks. In global carbon cycling, contaminant transport, local pH and alkalinity of terrestrial environments, calcite has some contribution In nature, it is also often found in doped forms with different metal ions. Actually, this is the unit cell of calcite. The unit cell of calcite is hexagonal and the space group is R3C. In the stoichiometric unit cell structure, the value of Z will be 6, so there will be 6 carbon atoms, 6 calcium atoms, and 18 oxygen atoms. Here we build our optimized structure for the MD simulation of calcite. The Vienna ab initio simulation package is a computer program for atomic scale materials modeling like electronic structure calculation. It computes an approximate solution by using DFT or Hartree-Fock or a combination of both. After optimizing our structure, we run MD on different temperatures like 300 Kelvin, 600, 850, 1000 Kelvin and 1500 Kelvin. Then we thermally optimize the structures and encode different properties of them. So first, the density of states. Actually, it indicates the number of states per interval of energy at each energy level that are available to be occupied. Here, this is the DOS diagram of our geometrically optimized structure. And after running MD at different temperatures, we got these DOS diagrams. So if we look carefully to these DOS diagrams, we can find that with the increment of the energy, the homolomo gap is decreasing. But up to 600, up to 800 Kelvin, we cannot find such significant change in the gap. But from that 1000 Kelvin, we can find the significant gap between HOMO and LOMO. Because the thermal decomposition of calcite completes about at 900 Kelvin. So after that, if the MD is done, you can find the significant HOMO-LOMO gap. And if you do the MD on higher temperatures, that energy gap is supposed to be decreased. Now the absorbance spectra. Actually, it is the light matter interaction. So if you, this is the absorbance spectra of our optimized calcite. The peak is in the UV region. If we, after doing the MD, if we look at our absorbance spectra, we look that there is not that significant change in the spectra, but the population distribution of the spectra is slowly moving towards the visible region. And if we do the MD at higher temperature, we hope that we can get the peak in the visible range, so that at that time we can get the color of the calcite. This is the MD of calcite at 1500 Kelvin. That's the video. Okay, so after that, we are inquiring the different properties of different doped calcite. One is the siderite. It is one of the most common doped forms of calcite. Here, the one calcium ion is replaced by one iron ion. So if we look at that, this is our optimized structure. And then we also study the DOS diagrams. Here is the geometrically optimized DOS of our structure, and this is the thermally optimized. This is the DOS diagrams of the thermally optimized structure. So if you look at that, here the total number of here the number of orbitals that are contributed by the iron d orbitals should be 5 due to the for the singlet ones, and for 10 for the spin polarization, and also for the 630 K Kelvin. And if you look at the absorbance spectra of the siderite, actually the most important thing is to do here, we should do the spin polarization for that, and I have a plan, I will do it in future. But for this absorbance spectra, we can assume that here the iron is in the high spin, or it may be possible that the crystal field splitting is very far from the ideal or high symmetry. Here the iron d orbitals are offset from each other instead of forming a region. And we can also see that here the iron orbitals are hybridized with the host orbitals. This is the MD of Siderite at 630 Kelvin. And that's another. Okay. And that's another form of the doped calcite. It is rhodochrosite, and we did the simulation at 630K and 750K Kelvin. And if we look at the density of states orbit DOS diagram, we can also find out that here the homolume energy gap is also increased with the increment of the temperature. And if we look at the absorbance spectra, we can find that the orbitals are separated into two regions here, and the DD transition is less intensive or almost vanishing here. So that's the MD of rhodochrosite at 750 Kelvin. That's all. So the main thing is that if we increase the temperature, the homolume gap between the calcite and different forms of calcite will decrease, so that we can hope that with the increment of temperature we can find the color of calcite or doped form of calcite, because in normal temperature calcite is colorless, but if we increase the temperature, if we find the calcite from very deep in the earth, we can find different colors of calcite. So if we do the simulation at higher temperatures, the homolume gap will decrease and we can get some colors of that.
Let's thank Faisal, and his presentation is open for discussion. I have one. So you are replacing which ions?
One calcium.
Calcium? Out of how many? What is the proportion of your transition metal doping?
There is 6 calcium ions in one unit cell for the geometric structure. So we just replace one calcium ion with one iron and one calcium ion for the with manganese iron for the rhodochrosite.
Can you show next slide?
That was for the rhodochrosite.
Okay. More questions to.
So I saw that the color of this material is changing due to the impurities, right?
Yeah.
Due to the whatever iron or whatever other transition metals you incorporate as a doping.
Yeah.
I call it doping, I would call it impurities. So I kind of completely lost what exactly is the role of temperature and why you so much dealing with temperature for these cases.
Yeah.
You don't see that you're changing your band gap when you introduce impurities?
But also in the case of pure calcite, if you do it for the higher temperatures, you can also get some colors, I think, because with the increment of temperature, the homolume gap is moving towards the visible region. So I think.
But do you have a physical reason why the gap is changing when you increase the temperature?
Because you may find calcite in different sedimentary environments, so you can get at 300 feet depth, you can also get in 2000 feet, and if you do much and much deeper, you can get the calcite. And due to this geological pressure and temperature, maybe there will be some the property change, so
right.
that you may get the
But
color.
this changes the crystalline structure, right?
Yeah.
But it's still crystalline, right? When you run your simulations at very high temperatures, you're probably losing your crystallinity. It becomes more amorphous, right? It's completely losing its symmetry. Is it? Like, especially when you go into 1000 kelvins, 700, 800 kelvins, I guess your structure becoming really very soft and not very similar to what you expect.
Yeah,
from
due to the high geological pressure and temperature, it may be possible the calcite may form into aragonite, and from aragonite to veterite. Yeah, there will be some sort of.
Have you been able to get this specific level?
No. I have not done the MD at that much high temperature.
Please note that this research was going on only for 2 weeks. and one cannot complete.
Right, but my point is,
Yeah.
I think that decreasing your gap is coming not because, like, it's not really related. I don't think you can really relate it exactly to this idea that, oh, it was formed at this temperature, so that temperature, that's why its crystalline structure becoming different, the gaps are different. It's just because you really introduce a lot of
Yeah.
disorder in your system, right? And you're having a lot of kind of this decrease in the gap coming due to the
Doping or
because you have a lot of disorder in your lattice, right?
Yes? You agree? He agrees. Let's thank myself for presentation and for discussion. And next presentation is by Zachary Gerers. He will be presenting an investigation of the catalytic reaction, so some chemical reaction facilitated by a catalyst.
Okay, hi. So my name is Zach. I'm sure you guys are familiar with me by now. This is good. So today I will be presenting my results on reductive nitrosylation, molecular dynamic simulations. So what is reductive nitrosylation? Well, it is a reaction where nitric oxide gets oxidized to nitrous acid, which then ends up reducing some metals such as iron. And so this process can be thermodynamically modulated, depending on pH and other factors that may impact the electrostatics of, let's say, the transition metal. However, my focus will not be on the thermodynamic properties, but rather the rate at which the reaction proceeds based off of dynamics. And in particular, I will be modeling the second step here and the third step. Okay, so why should you care? Well, nitric oxide is a very common cell signaling molecule in many life forms. And its interactions are principally with cofactors that are metallic, so like metalloproteins. So there is some physiological relevance to nitrosylation. What I will be attempting to do with these simulations, and I kind of briefly mentioned it, but it's to figure out what the optimal angle of collision is in order for the reaction to proceed. And the molecule that I will be using to exemplify this is this nitrosyl protoporphyrin 9, iron 3, coordinated with imidazole in the presence of hydroxide. Okay, so I performed molecular dynamics using VASP. I also used density functional theory to determine some density of states and calculate the CHEM orbitals. So, a couple of things real quick. The spin states in all of my models are singlet, so I don't have higher order spin states. And for the actual molecular dynamic model, it is charge neutral. All right, so this just shows the geometry optimized structure for my first model. The thing to keep in mind is that the HOMO has electron density on the porphyrin ring, whereas the LUMO has electron density on the nitrosyl ligand. If we look at the Sorey transition of this particular model, we see that these transitions are dominated by molecular orbitals that have charge density along the porphyrin ring. These are pi-to-pi star transitions that are commonly observed in porphyrins. All right, so let's look at a molecular dynamic simulation where the hydroxide kind of grazes by the NO. As you can see, we don't get a reaction. That may not be entirely surprising. But when we look at the electronics, it will differ from the model I had shown you before. So here, our HOMO, we have charge density now on the hydroxide, whereas the LUMO, once again, has some charge density on the nitrosyl ligand. If we look at our Sorey transitions, here, while our HOMOs, where the transitions arise from, are delocalized in the porphyrin ring, some of the LUMOs actually have some charge density on the ligands. So there's a slight difference there. Now, when we look at a molecular dynamic simulation where the hydroxide collides directly with the nitrosyl, well, we've noticed that, hey, we've not only connected, we've formed a bond, and it's dissociated from the iron. So we formed our nitrous acid. So what does that look like electronically? Well, our HOMO has some charge density on the iron center, which is slightly different from what we've seen before. And charge density now back on the porphyrin rings for our LUMO. More interestingly is that if you recall, with our Serre transitions, that those were in the LUMOs partially localized on ligands, and it's not anymore. It's back on the porphyrin ring. Another interesting thing is that if you plot energy as a function of time during the molecular dynamic simulations, notice is that there's this huge gap, or drop, I should say, in, say, potential energy or increase in kinetic energy for the direct collision. Intuitively, you would think this may actually correspond to either a bond forming, breaking, or some reorientation of the molecule being a kinetic barrier. However, at these time points, there are no ionic positions or atomic positions that can be related to forming bonds or breaking bonds. All right, so in conclusion, the hydroxide nucleophile here, when it directly collides with the NO, does proceed with the reaction. This is kind of supported that the reaction actually has happened by the reorganization of the electronics between where it did not undergo reaction and what it did. And one could state that the reaction appears to be thermodynamically favorable, but that may be an artifact in how the simulation was ran. And there's plenty of future work one could do with this on the kinetic standpoint or a thermodynamic standpoint. But one would like to relate reductive nitrosylation susceptibility to the iron 3 iron 2 redox of, say, proteins.
Okay,
Questions?
let's thank Zach for interesting presentation. Presentation is open for discussion. Any questions? I have one.
Of course.
You are telling that you have iron 3, iron 2.
Mm-hmm.
Is it possible, and what would you do to follow the change of the oxidation state of iron at each step of the reaction?
I would look at the partial charge densities of the populated molecular orbitals to see where they are located. So if they are primarily located along the iron center, then that would suggest that there are electrons there in orbitals that reside on the d, or the d orbitals of the iron. However, one thing I kind of skipped by because of time, and I can quickly educate, is NO is known as a non-innocent ligand. That is to say that it is difficult to discern what the oxidation state is of this iron center. So I may start with an iron 3, but the actual formal oxidation state of that iron can be iron 3 or iron 2, depending on where the pi star anti-bonding electron resides.
Okay. More questions to Zach? If no, let's thank him for detailed answering in the presentation. And the next presenter is Mendikantila Nakasinka. So he will present another mini research related to chemical reactions on the surface. But in contrast to previous speaker, he will look on the reactions catalyzed by solid surfaces rather than molecular catalysts. Okay, floor is yours.
Thank you, Dr. Dimitri, and good afternoon, everyone. Okay, thanks. So, my study is about catalytic electronic structure dependence on THIOPHENE hydrodesulfurization reaction. So, in petroleum industry, hydrodesulfurization is known as the process of removing sulfur contaminants from natural gas or crude petroleum products to form refined petroleum products. So during this hydrodesulfurization reaction, during this sulfur removing process, the sulfur contaminant hydrocarbon is treated with hydrogen gas in the presence of heterogeneous catalyst at elevated temperatures and pressures to remove to form this refined petroleum products, and hydrogen sulfide is formed as a byproduct. So here you can see a simplified catalytic hydrodesulfurization reaction mechanism in this diagram. So there are several theoretical and experimental studies have been conducted to study this hydrodesulfurization process, and in most of these processes molybdenum surfaces or molybdenum nanoclusters have been used as the catalyst, and THIOPHENE is used as the probe molecule to study this hydrodesulfurization reaction. So the main objectives of this study is to model the hydrodesulfurization reaction of THIOPHENE on molybdenum surface and study the dynamics of this hydrodesulfurization reaction, and also study the catalytic electronic structure dependence on this hydrodesulfurization reaction. So so in this study, as the model system, a THIOPHENE molecule adsorbs a single crystalline body-centered cubic molybdenum surface with 24 molybdenum atoms in excess hydrogen atmosphere is used, and the electronic structure of this model is determined using density functional theory, which is implemented in WASP software. And also molecular dynamic simulations have been used to study the evolution of the position of atoms during heat treatments. So THIOPHENE seems to be dissociatively adsorbing on catalytic surfaces. So catalytic surface, here you can see the variation of carbon sulfur bond distance during this adsorption process. So as you can see, with time one of these carbon sulfur bonds are dissociating. This bond is elongating and dissociating. So here you can see the carbon sulfur bond distance as a function of total energy. As the carbon sulfur bond distance increases, the total energy of the system decreases. That means the system tends to stabilize by dissociating this carbon sulfur bond. So this movie further illustrates the dissociation of this carbon sulfur bond during this the adsorption process. So this further confirms that THIOPHENE is dissociatively adsorbing on these catalytic surfaces. So here also we calculate the binding energy of this THIOPHENE molecule on this neutral molybdenum surfaces, and it is found to be 4.1 electron volts. So if we calculate the binding energy per non-hydrogen atom, it is about 0.83 electron volts, and it suggests that this THIOPHENE molecule is strongly chemisorbed on this molybdenum surface after adsorption. And also our calculated results are in qualitative agreement with experimentally determined data. So then we determined the catalytic electronic structure dependence on this THIOPHENE hydrodesulfurization reaction. So here you can see a THIOPHENE molecule adsorbed neutral molybdenum surface at 0 Kelvin. So at 0 Kelvin, only one carbon sulfur bond is dissociated here, and when the surface temperature is increased to 1000 Kelvin, even though this carbon sulfur bond is elongated, it is not dissociated, it is not completely dissociated. So this movie illustrates the dynamics of this THIOPHENE molecule adsorbed on neutral molybdenum surface at 1000 Kelvin. So at 1000 Kelvin, this carbon sulfur bond is completely not dissociating. That means this sulfur is not removed from this hydrocarbon, and it is not catalytically active to remove this sulfur contaminant from this hydrocarbon fragment. And we also did, so here you can see THIOPHENE molecule adsorbed on oxidized molybdenum surface. Moderately oxidized molybdenum surface. So at 0 Kelvin, like in the neutral molybdenum surface, only one carbon sulfur bond is broken. So when the surface temperature is increased to 1000 Kelvin, there are evidences of dissociating both carbon sulfur bonds. That means it seems like catalytically active towards hydrodesulfurization reaction, oxidized molybdenum surfaces. So this move illustrates the dynamics of this molybdenum THIOPHENE thiophene molecule adsorbed on oxidized molybdenum surface, and as you can see, after heating at 1000 Kelvin, this these carbon sulfur bonds are instantaneously dissociated at 1000 Kelvin. That means these oxidized molybdenum surfaces can be used as catalyst for hydrodesulfurization reaction. So as conclusions, thiophene hydrodesulfurization is depend on the electronic structure of the surface, and neutral surfaces are catalytically inactive towards hydrodesulfurization, and oxidized surfaces are catalytically active towards hydrodesulfurization reaction. And to remove those adsorbed sulfur and hydrocarbon fragment, we may need to further increase the surface temperature.
Okay, let's thank Tivan. And his presentation is open for discussion and questions. Students attending the course are welcome and encouraged to ask.
Is it getting points for this?
Yes. Okay, if there are no questions, I have one. So if you follow your own plan, the last word of your presentation, further increase of temperature to induce desorption of your products. What is your expectation? Which of the products will you desorb first? Sulfur H2 or
usually
hydrocarbon?
Usually sulfur have experimentally sulfur have some higher binding energy towards with the molybdenum surfaces. So I am expecting to remove hydrocarbon fragment first, so at lower temperatures than removing sulfur. So removing sulfur is equally energy required step like hydrodesulfurization process. So during hydrodesulfurization, it is equally known as removing sulfur from the surface, and also the carbon sulfur bond dissociation. Both are equally rate determining steps.
Okay. If there are no more questions, let's thank Tivan. Oh, okay. More
You
questions.
didn't really mention about your methodology. How you know that what functional do you use, what basis sets, and how you know that this will be valid for your system? Maybe your data are really affected by taking smaller bases, right? If you increase the basis, you will see that this happens not at bond breaking is happening not at 700 but much lower temperatures. Do you have any justification of the methodology?
Experimentally, this reaction is done at around 700 Kelvin, 700 Celsius. So that's why we use 1000 Kelvin. And the methodology, I am not exactly like.
What functional did you use?
Would you agree that you used PBE functional?
And actually, it was the same question to Zach, right, and to the previous speaker as well. And I looking on your reports, you explaining methods, but you're not given any details on methodology, what exactly functional you use and what exactly your basis set, what's the size of your unit cells, and so on. Okay.
Approximately, what is the size of your simulation cell? Approximately, how many nanometers or angstrom?
7 by 7 by 7.
No, nanometers. How big is your unit cell? How big is your simulation cell? Like it is of the order of the THIOPHENE molecule.
It's in the level of angstrom. It's like about 2 to 3 angstroms.
So the whole cell?
No, it should. I'm talking about the bond lengths of those THIOPHENE molecules.
But the whole simulation cell, how big is it?
Maybe about 4 to 5 angstroms. Maybe about 4 to 5 angstroms. I'm not exactly.
Maybe a little bigger.
Yeah.
Okay, let's thank Tivan for a good attempt to answer all questions. And the next presentation continues the subject of catalytic reaction. It is by Rhododchrosite, and I would like to bring to attention that this course was offered to both graduate and undergraduate level students. to bring the same level of technical skills and cover broader audience. Floor is yours for generous 4 minutes.
All right, I'm Brendan. I was looking at reaction between carbon nanotubes and hydrogen peroxide. A little bit first on all the different types of carbon nanotubes. They're split up into single-walled and multi-walled, but we're going to be using only single-walled and only one specifically because single-walled are much smaller. And then there's also a specific vector that is applied to the carbon nanotubes, which describes their shape. The single-wall versus multi-wall. Single-wall is probably your basic one atom thick, and multi-wall is pretty much like a single wall inside of another single wall, and so on. For the vectors that describe them, you can think of them as a graphene sheet, and then vectors along that graphene sheet point to another carbon that you would roll up into a tube and connect them there. So the 3 types that we could get when we do this are zigzag, where one of the pairs of vectors is a 0. So I've tried to highlight them in these pictures here so you can kind of get your mind around them. And we're going to be using zigzag, but there's also chiral vectors, where it's 2 unique numbers, and armchair, where both of the pair of vectors are the same. So we use the 4-0 that you saw earlier on the zigzag one, and we expected when we react it with the carbon nanotube, or the peroxide, that we'd get some formation of epoxides and carbonyls, as well as a burning reaction where carbon is removed from the carbon nanotube to make CO2 gas or something of the like. And this would make a hole on the nanotube. So we looked at this unit cell here, which is 2 units of the carbon nanotube long, and it has 16 hydrogen peroxides around it. And we ran a dynamic simulation for that. And one interesting part here, you can see the reaction between the hydrogen peroxide, one of the pathways here. The hydrogen peroxide breaks, and a hydroxyl group goes and forms with the nanotube, which is one of them that I did not expect to happen. And in this still frame here, it's kind of hard to see, but the 6-member ring on the carbon nanotube was functionalized with 3 different oxygens, and it actually broke and created a hole on the nanotube without dissociating a carbon off of the nanotube. I also looked at the system under both cationic and anionic states. The anion is here, and we see more reaction, but nothing like the cationic state where the whole nanotube kind of just breaks apart. And the ionic states we looked at are probably more than you might expect to find in a regular lab experiment, but it will give a good approximation of what we can do with a more limited time. So what we did see was reactions that I didn't expect. First off was the hole with no leaving group. We saw an epoxide form, and it was stable for hundreds of femtoseconds, but ultimately it did go to form a carbonyl. We kind of saw maybe a little bit of the burning with the cationic state, but not really anything like I had expected. And then hydroxylation and hyperoxide formation that I didn't originally expect, but we saw those as well. All right.
Okay, let's thank Brendan for a very interesting presentation. And this study of exotic regimes of reactions is open for discussion.
So I have a question.
Please.
Can you go back to where you have the charged species?
This one?
Which one is which?
Oh, this one's anionic and that one's cationic.
Why is it the cation?
So
How do
just
you create the cation?
well, the way we did it was artificially removing or adding electrons, but I think the thought is that could model
But
a Lewis
On a
acid-based
molecule,
system.
on each of the molecule, I mean, it's a single cation or
you and
what?
cell.
Oh, it's largely ionized, like more than 10 electrons, like 16. 16 out of like 300 or something.
So do you have any rationales between why one broke totally apart and the other one kind of didn't see much?
I think it was, and I looked at it, but it was a while ago. I think more of the electrons, like the change in this one came around in the solvent, and that one it was more on the tube itself.
So, for functionalizing your carbon nanotubes with oxygen, you can like directly use atomic oxygen. Was there a specific reason why you had to use like hydrogen peroxide to functionalize the carbon nanotube surface with oxygen?
That's just what I was looking at.
Oh.
No reason specifically, no.
Okay.
Would you consider this more as a gas phase or more like a liquid phase?
This was probably a gas phase because it was very hot, like at 2000 Kelvin. And, maybe it could be a liquid at really high density, like pressures, but gas.
Okay, let's thank Brendan once again. And the next presentation continues the subject of the electronic properties of functionalized carbon nanotube. And the presenter is Whitney Hong. So she will look more on the electronic structure side of the carbon nanotubes functionalized by oxygen.
Hi, I'm Whitney. So today I'll be talking about the oxygen adsorption on single-wall carbon nanotubes. So first off, I will go through the introduction and I'll talk about the motivation of this project, and then I'll talk about the methods, result, and then finally the conclusion. So first off, the introduction. A carbon nanotube is a folded sheet of graphene, or a sheet of carbon.
I just have a suggestion. Since he already introduced it, right?
Oh,
We probably
yeah,
can
sure.
skip it and save time for results, right?
Okay, and then some of the applications including electrochemical gas sensors, and they also use in polymers to control and enhance conductivity. They're added to anti-static packaging. So why am I talking? So for gas sensors, it can induce a strong change in conductance, and then the carbon nanotube can be used to detect gases such as NO2 and NH3 or oxygen, and experimental data has shown that oxygen increases conductivity. So we are using computational methods to look at this thing. So I use, to build and edit the models, I use Avogadro, JMOL, and VASView. And when I run the jobs, I use the VAS software. And then I use a 3-unit cell of carbon nanotube folded at 4,0, and I manipulate the position of oxygen on the carbon nanotube. So after optimization, I found out that the bandgap of the modified system definitely decreases compared to the pristine. This one, I have one of the carbon substituted with oxygen, and a few other cases where I have just I remove one carbon from the nanotube and just have one oxygen molecule on top of it, and the other one I just put either parallel or perpendicular to it just to look at the result. And the bandgap definitely decreases significantly. And then when we look at the absorption spectra and the molecular orbitals, for the pristine structure, we have absorption spectra at 0 frequency, but for other systems, they decreases significantly for the absorption spectra. Yeah. So in conclusion, the oxygen definitely decreases the band gap and thus increases the conductivity. The change in absorption spectra also proves that the oxygen is present.
Okay, let's thank Whitney for interesting presentation and for being broken short, which is very appreciated in our circumstances. And her presentation is open for discussion.
On one of your tables, you had log of A. What does that mean?
So So the A is the absorption at 0 frequency, but because it's too small to measure, so I use logarithm method.
More questions?
Could you provide more analysis, like you were putting this different alignment, different positions, right? And so you're saying, okay, electronic structure is definitely affected, but this is a very trivial result. You can say it without doing any calculations, right?
Yeah.
So you can give a little bit more physical or chemical explanation, like in which case, which one is why this or that, right?
So for sure we can see there's difference on, like the oxygen definitely affect the density of states.
Like when you compare, for example, substitution of oxygen versus just kind of attachment of O2 molecule, his absorption of O2 molecule, right? In both cases, your gap is decreasing, and right. But is it the same nature? Any difference in electronic structure between these two cases, or it's exactly the same behavior? In other words, can you differentiate these two cases just looking on your electronic structure somehow?
Not really, I don't think so.
But do you expect it should be different, or something should be different?
No, I was hoping to have more time to look at other ones, but I only managed to get this much information result.
But did you take a look on the orbitals localization? Maybe this could give you some ideas.
So
right?
for the HOMO and LUMO, it does not change a lot except for this one. It has localized orbitals on the oxygen.
In which case, when you substitute or when?
No, the one that I put on top, just the normal.
So when it's phase absorbed, then you have very strongly localized orbitals, and these orbitals introduce this closing or these sites inside the gap, right? In the other cases, when it's substituted, it's more delocalized over the surface, although the gap is still changing.
Yeah.
Okay, so you have a different nature of these electronic states. Okay.
Thank you.
Dr. Khan?
So what happened? So for the undoped system, it's a semiconductor, right? With a finite band gap, right? So that's true.
I would guess so.
How large is the band gap for undoped system? What is the gap?
Yeah?
Yes.
The
Approximately.
energy gap. The energy gap. Yeah, it seems to have a finite band gap.
You mean this gap?
No, here. From here to there.
In the pristine case.
So it's a semiconductor, right?
But
Yeah. Yeah.
what is the size of the gap? Approximately, like
You can look on your
0.1 electron volt, 1 electron volt, 10 electron volt.
2.
Okay.
Yeah.
Around 2 electron volts.
So about 2 electron volts.
Yeah.
So what happened when you put some species on top of it?
It
So the system is still a semiconductor, or it become a metal?
It's a semiconductor, but I believe it's a semiconductor.
What does happen to the gap?
It decreases.
But it
would
still exists, right? It's not completely going to zero.
Yeah.
Okay.
So it's still a semiconductor.
But then, whether it's a semiconductor or not, it also depends on the position of the Fermi level, right?
Okay.
But you are telling that it is not going to, it doesn't transfer to the metal.
No.
It is still a semiconductor.
Yeah.
At least what you found. Okay, but thank Whitney once again. So we have Next speaker is Jabet Abu Mohammed. So please set up your presentation, and he continues the description of the electronic structure of nanomaterials, and he will be looking on the interface between metal and semiconductor. We have 4 talks for about 20 minutes.
And this is going to close at 2 p.m.
Yeah.
So yeah,
Yep.
we have more time. So I'm going to talk on the initial state of the metal and metal interface for resistive switching applications. So since the resistive switching is a new thing, some guys. So first, let's start what is actually resistive switching. So if you're going to start on the electrical, they have a 4-parameter voltage, flux, and current and charge. So if you're going to make a relationship, we got a 3 different circuit, but still they have a 1 relation between the charge and flux missing until 1971, or in the Dr. Liu Chon, he mathematically derived an equation and formed that maybe there should exist a circuit which is called a memristor, and is practically prepared in 2008 by HP scientists. So how this actually switching is work? So is the device, if we increase the voltage in a positive direction, the conductivity will increases, and it can keep memory that conductivity. And if you put the reverse bias, it will give you that previous resistance. So we are going to make devices with these properties, but question is why we need these properties. So in a one sentence, this recent semiconductor-based technology, it's almost in the theoretical limit up to so we need new mechanisms. So it would be the replacement of these devices, and it can be used for like neuromorphic device designs. So to do this one, I consider my models. My models actually, I am considering one titanium oxide layer with one of the metal oxide layer on the top of them to study these properties. I studied this system on the bulbs using methodology. To do that, this one is giving us a pristine only metal oxide layer with the metal, and this one is I replace one titanium with the aluminum in the titanium oxide layer to see how it changed their conductivity. I also studied with the oxygen vacancy, how it changed the conductivity, but I didn't actually complete on this system, so I just work on this too. So first one, this one is giving us a 2D presentation of the orbital, how the electron localized in which part, in which layer, metal oxide layer or in the metal layer. So this one is showing the pristine one, and this one is showing the with the aluminum doped one. First, if you look on this lattice structure, by doping aluminum, the lattice structure is distorted much, but this one almost showing this pristine titanium oxide lattice structure. So in this case, HOMO -1 and HOMO, there was some electron delocalization on the metal part in here, and this in the LUMO too. But when I dope aluminum, this electron is moved towards the oxide part, and also LUMO, it's also showing the all electron transfer to the LUMO layer. So maybe because of this oxygen, it could introduce a charge transfer in this here. This one is just an orbital showing of these two previous one, as shown in the previous slide. This electron almost localized on the metal part. In the LUMO is metal part with oxide layer, but in this case of a doped system, this electron is localized on the metal part also. And this is some kind of other presentation of previous slide. But when I take a dose, it's showing that this one is for pristine and this one is for with the metal dope. In the pristine, it's showing that there have a overlap between the Fermi. This is the Fermi level. This is occupied on the. There is some metal characteristics, but there are some significant, energy difference in the HOMO -1 and HOMO low energy state. But when I put the aluminum dope, is giving us a more continuous, orbital, occupations, and also the overlapping of the unoccupied by electron is higher than the undoped system. And these two, I optimize by using the electric field towards the Z direction. Z direction means from here is the metal part to the, metal oxide to the metal directions. In that case, I saw that this one in the undoped system, by applying the electric field, it didn't change the energy level that much. But in this doping system, it increased the occupation of the unoccupied orbitals with the electrons. Excited electron is much more than compared to this one. So from this DOS calculation, I can say that very good. This one is that because of doping, under the electric field, it changed the occupation number is huge. So doping change can lattice the change significantly, but most important result is that doping helps to increase the conductivity by minimizing the energy gap and increase the occupation number in the higher steady state. So, but I didn't do much work, so there have some feature work too. I need to do the PDOS and DOS.
Okay, let's thank Jabet for the presentation. Questions?
Can I see the supercell model again?
This one?
I mean, a lot of disorder, yeah. So, what happened? Do you think that's reasonable? Maybe the number of layers that you have maybe is not large enough, or you see exactly what you want. So you want to have a stable, some bulk-like layer, or you want everything kind of,
No, I want a stable one layer, and which will increase the conductivity. If I apply the, which will change the resistivity if I apply the current.
So
that's my.
So you're trying to model more like a thin film, right?
Yeah.
Right. So I would assume that with a thin film you have a bulk-like region, right? Inside the thin film it should be like in a bulk system, right? And near the surface you may have surface reconstruction, surface relaxation, or whatever, right? So it seems that your system is not, good enough to see that. Another thing that you can do is, in addition to adding some more layer, you fix the middle layer to at least, 3 layers in the middle. Fix them at the bulk lattice constant, right? So in order to meet the bulk layer in the thin film, right?
So my another aim is actually to minimize these device sizes. So if I want to make another layer, it will mimic the bulk sizes, but I want to make a smaller devices. 2D device, two layer, one layer.
Okay. So you want very thin.
So then I can make a bigger number, many number of devices in a small pieces. That's also important for this one.
Have you considered tunneling?
Yeah, I have to. So I cannot make it more smaller. So that's why I need to optimize.
But is this big enough?
I want to minimize tunneling because if I get the more tunneling, it will become a conductor. So we need to optimize tunneling and Scott-Keegan barrier too.
Okay, but we should be short.
How do you incorporate electric field into your system?
In books, there have this one, but do you want methodology? How do you use this one, or how do you calculate this one?
There's a strict methodology that you have to follow.
Yeah.
Is that in your?
Yeah. No, I didn't include that one here.
Sounds good.
But I do have. I can, if you want, I can read it.
Okay, let's thank Jabet once again. And we have third.
Dimitri, we just received notice NDSU will be closed at 2 p.m.
Yes, we will be finished before.
Okay, just to let you know.
But thank you much for bringing it. So, we have 3 presentations more, and the next is by Samuel Brown, who is at the Department of Polymers and Coatings, and he will make another presentation on metal nanoclusters and their optical properties.
Yes.
Floor is yours.
Thanks, Dimitri. As you mentioned, I'll be exploring the oxidation states for optically active silver nanoclusters. So to begin with, I'm just going to describe silver at different length scales. So here you can see we have silver in the bulk, just a silver metal block. And then this, if you look, is a TEM image of a silver nanoparticle that's about 6 nanometers in diameter. And then here's the model that we'll be working with later, a silver nanocluster that's only 13 atoms total. And then here's the representative density of states for each one of these models. So just kind of for reference of what we'll be looking at. So because the density of states becomes discretized for the smaller nanocrystals, that allows for different optical transitions. And then work by Diaz and Ross showed that, one of the papers showed that you can actually get fluorescence from these models. And then with the nanoparticles that are slightly bigger, you can get surface plasmon resonance, which alters the absorbance properties. In this presentation, though, we'll be focusing mainly on the silver nano clusters, the very small ones, that can be optically active. So here's a molecular dynamics room temperature of the model that we'll be going over. So it's a silver nanocluster with 13 atoms making up the core of the silver, and then it's passivated with 12 cytosine molecules. So typically when they synthesize these in the lab, they use DNA as a scaffolding material. So for this case, we're using cytosine as the representative scaffolding.
May I interrupt you right away?
Yeah.
Do you know the structure? Is it known experimentally for that it's really 13 atoms in the silver, and also what the conformation silver has? Is it experimentally known, or you just took this structure because you need some to
I think
start?
something just to start with.
Okay, so no experimental data on this.
Yeah.
Okay.
So what we wanted to do first was just explore the different oxidation states and charges of the system to see if we can find a lowest energy. And when we did that, we found that the lowest energy was at a charge about negative 500, which is extremely low. So we decided to kind of explore different areas. So we went and looked at the charges around the neutral state. And looking at this, we can see that we get a deviation from the parabolic function we saw earlier to a quadratic function here with a inflection point around -6. This inflection point doesn't give us a whole lot. I looked at density states around it, and it seems to be similar. But looking at these models, we then explored the band gap for these ones, which is here. So I didn't mention we looked at different spins of 0, 1, 2, and 3. So this is spin 0, 1, 2, and 3. And then we looked at the band gap for all these different oxidation states. And for high oxidation states from about 3 to 10 in these models, we can see that the band gap considerably widened to about 2 eV. And since we did this for both alpha and beta electrons, we multiplied the band gap of the beta electrons by -1, so that's all we have a negative band gap here. Looking at the models that were optically active and had a band gap in the previous one, we then we plotted the band gap, the HOMO-LUMO energy for these different states, which is here. So you can see for a higher oxidation states, +11 compared to +5, that both the HOMO and LUMO energy drop, and that's pretty much independent of the spin of the system. So for now, we're just going to look, in the interest of time, at these two different spin states, the optically active systems where both the alpha and beta electrons both have band gaps. So looking at the density states of these systems, you can see that, as we'd expect, all the electrons are within the conduction or the valence band, and where if you excited it, they would jump into the conduction band, and you'd expect to see some sort of fluorescence or something like that. And then if you increase the charge, so you're increasing or decreasing the number of electrons, you lose state. So that's why it looks like it's more discretized in these cases. So we're now going to look at some of the optical properties, absorbance, and some of the different molecular orbitals for just this specific model. So looking at this, we determined the oscillator strengths for that, and using this equation here, we can develop an absorption spectra using these oscillator strengths, which is what we have here. And these vertical lines indicate the 4 strongest oscillator strengths, so the 4 most probable transitions, which are also listed here. So looking at these, the molecular orbitals of these 4 strongest transitions, we see that for all the lower energy states, so this is where the electron would first preside before it is excited, that all molecular orbital resides right around the core of the silver. But then when we excite it, it jumps to a molecular orbital that resides predominantly on the ligand. So this kind of gives us an idea that not only is the size of these silver nanoclusters and the charge important to the photophysical properties, but the ligand itself is also plays a role in the fluorescence. So just a quick conclusion. We have a silver nanoparticle. We looked at the different energy, and we found the minimum to be around -500. But then we looked further near neutral states. We saw that several of these would have a band gap open up, and then we looked at it and found that the ligand played a critical role in the fluorescence. So
let's thank Sam for nice and brief presentation. And questions are welcome if they are brief. Yes.
It's a quick question. I mean, in one slide you saw that the charge is something like 500 or something. What do you mean? So you start with the then you dump in 500 electron into the
Yep, that's what we do. We just put in a bunch of electrons. So
that's a huge number.
So I first started out just why I did that. I started around here and I got this, and I thought that it would kind of come back up in a parabolic. So I wanted to try to find that minimum energy. And as I kept going, it kept going down until I just started dumping in tons of electrons. So I found the minimum, but is it physically relevant? Not really. So it's just kind of what it is.
Okay, let's thank Sam once again. And we have 2 talks for 10 minutes. So next presenter is Aaron Forde, who is also in MNT
10 minutes.
program.
20 minutes.
You better plan to finish 10 minutes. And I suggest that we make a group photo before leaving, after all presentations. So he will be telling about new materials which are becoming famous and favorite for photovoltaics, so-called lead halide perovskites. Floor is yours.
Hello everyone, my name is Aaron Fordy, and for the next couple of years my research will be involved looking at the charge transfer states for photoexcited transitions. So for my project I decided to look at the charge transfer states between lead halide perovskite and organic dye molecule. So motivation, why lead halide perovskite? So the biggest motivation is it shows a lot of promise for next generation photovoltaics for like dye synthesized solar cells and thin films due to its well-aligned band gap, its high absorption of visible light, and its ability to transfer charge carriers long distances. So since it can carry charge carriers long distances, it can act as either an electron transport material or a hole transport material as well. So it's pretty versatile in that way. So then what we need to do is we need to find molecules to pair with it to extract either the electron or the hole out of it to do spatial separation of the charges so that we can run them through the circuits of the solar cells to get power. So for the models I use, specifically I use cesium lead iodine perovskite, CSPBI3. And then for the organic dye molecule, I just chose triphenyl nitrogen because it's the simplest dye molecule I could look at to begin with. And then for the input atomistic model for VASP, I chose a CSA-PB8I24 slab. So it's a couple unit cells that has a surface, and then it extends periodically into the structure to mimic bulk characteristics. And then we just place the dye molecule. It's not physically connected, it's just placed pretty close to the surface of the perovskite. And just to know that all of these conclusions, they were done at a ground state optimization, so it's all 0K, so there's no thermal fluctuations with these results here. So if we're looking at the spatial distribution of electronic charges, the right table shows the electronic transitions between orbitals I and J, so HOMO -2 to LUMO +8 state, and then the oscillator strengths for that transition, which gives the probability of that transition occurring, and then the transition energies for those transitions. So for this first one here, for the HOMO -2 to the LUMO +8, we can see that there's not much spatial charge separation because it's basically just jumps into another region of the perovskite. And that kind of makes sense that it has a high probability because when you look at the oscillator strength, it comes from the transition dipole, which is the oscillator strength is proportional to the square of the transition dipole. And the transition dipole is basically a measure of the orbital overlap between transition states. So it makes sense that the highest probability one would be spatially close regions for transitions. But then if we look at states that do produce spatial separation of charges, like our HOMO and LUMO state here, where the electron would reside on the perovskite and the hole would reside on the HOMO, we see we do get charge separation there, but has a very low probability of occurring due to there's not much spatial overlap between the orbitals. They're on different sides of the materials, basically. So to summarize that, the most probable photo-induced electronic transitions occur within the perovskite, and they don't produce charge separation. While the transitions that do result in spatially separated charges, they have a very low probability of occurring. So we have to consider a different method to get spatially separated charges. So on the left, this shows the photoexcitation from the HOMO -2 state, which leaves a hole, to the LUMO +8 state where the electron would reside. And then if you think about it, that this is a very unstable state, and then the electron will want to come back down and try to get into equilibrium. And to do that, it will relax to the band edges, which happens approximately on the picosecond level. So if both electron and the hole come to the band gaps, that will produce spatially separated charges. So to show this conclusively, I would have to do the charge transfer dynamics of this system as the next project to follow up on this. So in conclusion, photo-induced electronic transitions themselves are not enough to generate charge separation. We need to consider the relaxation processes after the photoexcitation to the HOMO and LUMO gaps, where the electron would reside on the perovskite and the hole would be on the organic dye. So the organic dye acts basically as a hole transfer material. And then as a bonus, just a little simulation. As you can see, like the organic dye is it moves around a lot, and then the perovskite is very heavy, and if you look close enough, you can see some of the modes that move. And then for the next iteration as well, we would bind that molecule, place some functional groups on it, and bind it to the surface.
Okay, thank you, Aaron. So, questions?
I completely miss your motivation, because perovskites are known to be used just by itself, right? And getting right away 20% efficiency in solar cells, right? Means it's already providing the charge separation without any additional molecules on the surface or anything. What exactly is the purpose of getting this molecule on the surface of perovskite? Oh, I did miss the main point? Or what?
As far as the literature
what is exactly your motivation?
The literature I've seen is that the perovskite, it can act as itself to separate charges. It has an internal electric field, but that's for methyl ammonium, which with the internal cation, it can create internal electric fields. But for cesium, it's just a charge.
Oh, and yours was not lead, it was cesium?
It's lead, but it's cesium. So if you look at so for other, the methyl ammonium ion would be in the middle, and this one's just a cesium, so it's just a static charge, where with the methyl ammonium, it can create internal electric fields.
Okay.
So for this one enough, it wouldn't create internal electric fields to separate the charges.
So you modify the lattice of your perovskite, kind of taking the molecule which is known that it's not very ligand, which is not very favorable in terms of charge separation, right? Mm-hmm. And you trying to improve this charge separation? I lost the point.
Let me reformulate the question.
What exactly are you trying to address? What question are you trying to address?
Would you say yes or no for two opposite situations? One, perovskite material can be connected to the leads of the same material and will generate electricity. Second statement, materials that are leads must be of different nature, different Fermi energies in order to support current. Can you use leads of the same material of the same nature from both sides, positive and negative? Or they should be different?
Oh, it's a question to him?
It's a question to the speaker. In solar cells, can you use N and N or P and P doped silicon? Or you need an interface?
You need some sort of interface to produce the electric field to separate the charges.
Can you make connections to this?
So in this case, even though the cesium is charged, it doesn't create an electric field like the methyl ammonium would, because it can rotate and it can create little ferroelectric highways for the charges to kind of separate. So in this one, there's no net internal electric field to separate the charges. So we need another molecule to pull one of the charges away.
But other type of perovskites exist where this internal field is good to have, right? Just because you having the right ligands there. Am I right?
Mm-hmm.
And these perovskites have been shown really good promise for the solar cells. The question is, what exactly the benefits would be to take these other ligands, which already know not beneficial as ammonia ligands, as you mentioned before.
Mm-hmm. I think
methyl ammonium don't decompose.
Wait. After you generate solar cell out of perovskite, to remove charges, positive and negative, you need hole transferring material and electron transfer material, which are
this is your
different.
LEDs, right? You're just taking your different LEDs and they will...
You are connecting it to a metal.
Yeah.
And before you connect to metal, you need additional materials. And they're different on different biases. What do you comment on this?
Yeah, so you need to separate the charges before they can migrate to the electrodes. So like if you see here, like if you just separate these two charges, they're gonna want to come back together instead of separate.
So you want to remove charge from your perovskite?
Yes.
Somewhere away. Selectively remove which charge, positive or negative?
Either one, as long as.
But here, in your work, which
here the hole
charge
was
are you?
taken out.
Huh?
And here the hole was taken.
So you're removing positive charge.
Yes.
Only. Okay. There was very briefly.
Yeah, that's almost same question. Now, what's the direction of the charge flow? Is going towards the dye, or I mean, you're separating hole and electron, right?
Yeah.
What is the direction of the hole? And
So this would be the hole, because if you photoexcite an electron, it's going to be above the band gap. So when it comes back down, it's going to be on the LUMO. And the LUMO's
you
out.
said they are not physically connected. I mean, they are not bonded. So what's the mechanism of charge transferring to or hole transfer towards the?
Right. This one's not going to be the most physically active, but you can kind of see they're close enough where you can get some sort of tunneling between the
Then
charges.
how can you move the hole to that?
Oh,
dye?
then this would be connected to another dye molecule. This is just a short segment of a dye molecule, but in reality they're bigger organic molecules, so it'll transfer through that molecule, and it's going to take the least conductive route, so it'll just keep going through the molecule to get to the electrode.
Good. Let's thank Aaron and all audience for the discussion. And we have last presentation by Levi Lustrom, who will continue the same area of research, the photoinduced charge transfer at the interface of inorganic and organic materials with some specifics and some interesting analysis.
Okay. Thank you all for sticking around. Today I'm going to talk about two different dyes and the rate at which holes will be taken from the quantum dot. So the motivation behind my talk is we want to put it inside of a solar cell, and there's several things that need to occur, but the things that I'm interested in are the rates at which the electron is taken from the quantum dot in the hole. And we want the hole rate to be faster than the electron because that helps the system be more efficient. So to do that, we want to try and find ligands that will extract the hole from the quantum dot. And there was a paper by the Weiss's group where they took the same acceptor and they linked it through two different linkage groups, one being PTC and one being BA. And I'll just say the first one, not the entire one, the entire name. And PTC has been shown to very well interact and couple with the quantum dot, and it makes the absorption spectra redshift. And you can kind of think of that as the particle in a box. The box has got slightly bigger because it interacts with the sulfur on the group.
And again, what's the difference between your linkage just because so small?
Oh, sorry. So it's sulfur for PTC and oxygen for DMA. So
it's carboxylate and the
sulfate group? Yeah, so that's the only thing that's different, is the oxygen and sulfur. So this is my system. I have a totally neutral, so I have 33 cadmium selenium quantum dot, and then I have my full ligand with an extra cadmium, and then I took a reduced model of the ligand to keep it charge neutral because these systems typically are charge neutral, and we don't want the charges to close the band gap. So the methodology, just like everyone else, I use VASP with GGA, functional PBE, and my main tool in this is when we collapse the CHEM orbitals into either one dimension or just, two dimensions. So we have Z and then the amplitude, or just the center of mass. And that's given by these equations. So in the experiment, they excite at 2.95 electron volts. And if we look at the states that are important around that region, we can already see the difference where for the PTC, we have some states that are very charge transfer in nature, which would mean that we already broke our exciton into the electron and hole, so then the hole can be extracted very easily. But for the BA, none of the states are that charge transfer. And how we get this is if we look at our, this is the different states, and then plot the center of mass, and we can see here that there's, it's localized on the ligand, and then everywhere else on top is localized on the quantum dot. And we can see that a lot of the PTC are excited, the hole is in this region. So the BA has to relax down to almost a HOMO level to be able to get a charge transfer state. So this is very important because we want to see charge transfer. So from this diagram, we can make a conclusion that PTC facilitates charge transfer because it's either initially excited to a charge transfer state, or it has very few states to relax to get to a charge transfer state, where BA, it has to relax almost to the HOMO level. So then this is just a partial charge density of the highest charge transfer state. So this is 353, and we can see that the charge transfer is only on the ligand, and there's no localization of the hole on the quantum dot. So in conclusion, we can conclude that PTC facilitates charge transfer because it is either initially excited to a charge transfer state or it is very close to a charge transfer state, where BA has to relax down to a charge transfer state, which will increase our rate for hole extraction.
Okay, let's thank Eli for his presentation, and his presentation is open for discussion and questions.
Yes.
Yes?
Okay. How did you create a quantum dot? I mean, not really a quantum dot, it's more like an atomic cluster to me, because quite small. But
so for these, back in, I think, around 2010, there was a paper that described ultra small quantum dots, and the most stable was 34, 34, or 33, 33. So these are experimentally available, and how I did it was I took bulk cadmium selenide in the Rhodochrosite crystal lattice, and I cut a sphere, and then optimized it.
You started optimization, no MD simulation. No.
Yeah, so I took a already optimized quantum dot because in my research I used quantum dots, so I already had it optimized. So I didn't start from bulk and then have it optimized.
More questions? More questions, one?
So you're saying that you excite to the state which is more energy transfer character?
Yes.
But if it is energy transfer character, then its intensity is probably not as high as just pure quantum dot transition, right?
Yes.
So means this, you didn't show the I didn't see the spectra comparing both of these structures, right?
This is the spectrum.
So the spectra are not very different.
No, and it's probably due to the fact that we only have one ligand on the surface, so we didn't get a huge redshift of the blue one, but we do see that the blue one is a bit redshifted.
Okay, but actually where you excite, it's mostly quantum dot transition, right? Which is just a little bit hybridization with a ligand.
So these are the oscillator strengths from around where they excite. And these are the states that contribute the most. And we see that, although this is not
and this is based on VASP calculations?
Yes. So without...
Do you really trust these calculations then? And this
there might not be, because we could need to include Coulombic interactions, because these are independent particle.
Approach, okay. Okay.
Okay. More questions 1. More questions 2. More questions 3. Okay, let's thank Levi. So, I would like to thank everyone for presenting, for supporting the discussion. The course was containing 3 components: methods, practical skills, and scientific communications. Also, everyone in this course has completed brief paper, and I think it will be a good appetite for computer-enabled research component for your experimental. Before we leave, I would like to suggest 2 things. Please bring to me your forms if you were filling them, and let's gather in this area and make a group photo within a minute. Okay, please come up front.
And you technically have 2 minutes, right?
Yes.
Because at 2 o'clock there would be some other class here.
No, at 2 o'clock Andy is proposed.
Do you need to? Do you have another class?
No, it
is cancelled. Another class is cancelled, right?
Yeah. So our test is next.
It's cancelled.
Lucky you. So you may hold your just in front of screens.
How are you? Are you still with sequence?
I moved to the physics.
Oh,
Guests are also invited to come and take picture. Please come. Please come.
Are we going to take it with that?
No, we can actually.
Why not?
I also took the quantum chemistry.
Oh, good. Please gather here. Take some decoration. Come to the center. Yeah.
I thought about
Oh, please, would you like to join the photo?
I'm not belonging to this class.
You do. You were participating in the discussion.
You are.
She could take the picture.
Oh, Levi.
Oh, okay.
I feel like we have better camera.
Come to the center. Consolidate to the center.
Consolidate.
We are in frame.
Okay, look at me.
Stand in the windows.
1, 2, 3. That's very slow. Okay. 1, 2, 3. Okay.
And do couple more just in case.
How to? Okay, I got back to the camera. All right, 1, 2, 3. Okay, that's pretty good.
Okay.
All right. Nice.
Thank you so much, and many thanks to everyone. So the meeting is dismissed. Everyone gets very ready for just coming and presenting. And based on what you do in the forms, there is a chance for even higher grades.
So you didn't drive?
No,
You
I
took some
didn't.
bus?
Yeah.
Oh, wow.
From our building.
I really did not.
You mean
want
the research?
I really wanted to take my test today. I just wanted it over and done with.
We have to Hey, dude, sorry, but I managed to pull I hope I'll try to get credit for
I emailed him like, hey, that Joey's for taking the test, and then he was like, taking the test. Which I don't know how Francisco or how it is his name can take it, because I thought he was leaving on the plane. No, I think Thursday he was leaving for India, or wherever he was going.
Was there coming in? Bad out there.
I heard yesterday that from 9 a.m. today until all night there's supposed to be a winter advisory.
But I thought it. there was like a blizzard advisory.
Take some time, but you might be
If you go from like Fargo up about 30 miles and then take like an angle all of North Dakota, blizzard. Here we had a weather advisory. They had a blizzard.
Yeah, but it's not so bad, right?
But I'm an hour.
See you around.
Right, so like that. Okay, Dimitri. Thank you. See you.
Thanks much for coming. Thank you for supporting the discussion.
I'm going to talk about HPC in the physics department tomorrow. So.
Which time?
I don't know. 3?
Can you send me a reminder?
Yeah, I can send it. Graduate students.
I think we're gonna look at buying tickets for
So means
Wait, so you're driving there?
No. Plane.
So
Well,
keep a home
because
right? So
I'm at least for me, I'm gonna drive to Minneapolis because from Minneapolis to either Jacksonville or Berger or whatever that one is, it's like $150-200 cheaper. And my brother lives like a mile from the airport, so like I could be like, hey mom, you drive us. And then we don't have to pay for this. Like parking. And if there's 4 of us, it's no brainer.